Right. So you might have already played with different versions of different Rayleigh numbers, different viscosities. And it turns out that you can actually look at the results and check if the computations are correct. Namely, the Rayleigh number changes the structure or the type of energy transport that is going to happen from bottom to top in our box model that you ran. And we can look at how efficient the heat transfer is by looking at the heat flux at the top of the boundary. So how much heat is flowing out by whatever is happening inside. Okay? And so the Rayleigh number is basically, the higher you pick the Rayleigh number, the stronger the convective part of the transport becomes, because it becomes a more effective way to transport the energy. And the Nusselt number is basically the heat flux out of the top surface, and we're going to look at this number, and with that we can tell, based on the Rayleigh number, what Nusselt number do we get. And, well, turns out there's a relationship, and we'll try to see if we can get that in a minute. Okay? There's also certainly a problem. For those of you who've played with the standard mesh, you crank up the Rayleigh number, which means the convection gets more vigorous, which means the plumes are getting smaller or thinner, and at some point you cannot resolve the features anymore, and you need to go to a finer mesh. And we already talked about this kind of already. But so for that, we kind of need to look at an output, and we need to look at statistics. So you already looked into the output directory, and you looked at graphical output. Turns out we generate a lot more output. Log.txt is what's getting printed to the screen, and if you look at it, you can actually see the heat flux that we're going to look at later on, namely here, heat flux through the boundary parts. And this is not very descriptive, but this is left, right, bottom, and top, right? So we have a negative flux out of the domain at the bottom because we have an influx. And this is the positive number, which is the outflux of the heat at the top, given in watts. Assuming that all the other units you typed in are actually units and not a 1x1 box or something non-dimensionalized. Okay. Why do we have outflow or inflow on the sides, even though we kind of wanted to isolate things? That's not good, isn't it? Right? We picked our boundary conditions to be. Let's see. Did we talk about the boundary conditions? Not sure. Let's go to them. Okay, so we prescribe 2 and 3. That's actually not very helpful, but it's described in the comment above. 2 and 3 is bottom and top, so we prescribe the temperature of the top and bottom, but we make the velocity tangential. So that would mean that there's actually nothing that should flow out on the sides. So what's going on?
It's tiny.
It's tiny. Yeah, okay. It's like less than 1,000th of the stuff that flows out at the top and bottom. Okay, so is that okay? Is that acceptable? Can we fix that somehow? Maybe. Yeah, so I don't know. Maybe solving the linear systems more accurately would actually bring this number down. I'm not sure. All right. This is quite coarse. It's like 3 refinement levels. 4. Yeah. How is it for you?
About the same.
Not the same.
Just like 1.
All right. If somebody wants to play with it, there's a linear solver tolerance. Maybe that influences that. But numerically, it's much smaller, right? Okay. So I want to show you the statistics file, but I got sidetracked. So here are the graphical output files for the particles and the solutions for each individual time step and also for each processor. Not that we are running on multiple processors right now. There's also another file here called statistics, and I'll just double click on it. And so this is a text file, and what it basically contains is simple statistics for each time step. So you see here, this is like one line is, well, it's longer than one line because it's wrapping around, because it doesn't fit in. So this is time step 0. How do I know this? Because there's a help at the very top that tells me the first column is the time step number. The second one is the time. So, okay, this is time step 0, this is time step 1, and then there's all kinds of other information, right? So I can actually go back and look at the output here. So, for example, we have this number here, which is going to be our Nusselt number that we're going to look at. And in the statistics file, that number is column 20. And without having to count which one it is, it's the last one. Right, so this is this one here. 2.1891, whatever. Okay? So why do we output this in such a format? This is really nice because you can very easily visualize, post-process, look at things. For example, if you want to know if the solution already converged, you can look at things like a root mean square velocity and see if the velocity becomes 0 or if the velocity is changing or something like that. So if you want to know, at the end, when we reach a solution that doesn't change anymore, so I can just go scroll all the way down and look at the last number here. And this is my Nusselt number that I got from my computation. All right? So going back to the slides, now you finally know what you have to do. Okay. Oh, you can actually plot this. That's very convenient. So I'm showing you that. So if I go in the output directory, there's the statistics file that I showed you before. One thing I might want to do is I want to plot, for example, the outflow at the top over time in years. So my x-axis would be column 2, and my y-axis would be 20. You could open this up in OpenOffice, plot something, use matplotlib, your favorite tool, whatever. The easiest way to do this is GNU-plot, because I can just say plot statistics using 2:20 with lines. And if I don't make a typo, statistics, then you'll see what happens. At the very beginning, if you remember how the animation looked like, there's no heat outflux at the top because heat first needs to come in at the bottom, right? And then the big plume hits the top at some point, so we get a gigantic heat outflux for a while, and then it settles down to a constant heat outflux. So I guess that is a valid solution that doesn't change anymore over time. I can also plot different things. So if I go back in here, I can plot maybe the root mean square velocity, which is 11. If I can find this. Right? That also seems to settle. But for example, if you had something that is no longer stationary but stays unsteady, then you would see changes whenever plumes like hit the top or bottom. All right, does that make sense to everybody, what I just did here? So this is just on the x-axis plot the time, on the y-axis plot the heat outflux at the top of the box. Could plot other stuff too. Like 19 is the influx at the bottom. Not sure that is interesting to see. And I made a typo again. That also seems to settle somewhere. Questions so far? All right. So now what we're going to do I kind of answered the last question already, right? Okay. All right. So now I will split you into groups if you haven't done so yet. And what you need to change is we are going to modify the viscosity so that we have a specific Rene number, and we computed those already for you. Then you run the computation, and you should also change the end time to what we suggest. And then we'll collect the numbers that we have. Okay? And as I said, the Nusselt number is the boundary 3. And I have prepared a table for this. So I'm not sure if I already did one of these numbers. What was the default setting? We can check that. So my viscosity is 5 times 10 to the 24. And that is actually not in this list. Okay, so I guess you have to do computations. And we actually need it for 3, 4, 5 because it turns out, at least here, we're going to need 5 fundamentals. So does anybody already have numbers to fill in? Is anybody still running, or do we have any blanks here? I would like to fill these in, and then we can plot the result. Yes. All right. Which one did you do?
1.02E23 minus level 5.
This one?
Yep.
Okay. What do you get?
I get 3.085 6986 e to the 5.
You probably don't need that many digits, but you can actually check if this number is converged yet by looking at it.
I know,
It's okay. Do we have any other numbers? Sam, yeah?
For the 523 for refinements, it's 1.9445 times 10 to the 5.
All right. I can try to run one of these so you know how it works. So change this. Maybe I make the one at the top left because that's quick.
Guys, do you want these questions? Please. I'm wrong.
And we also gave a suggestion for the end time, because if you're not running long enough, then it will not be converged. One thing I haven't mentioned yet is when you run it, at the very beginning, it will show a list of things, and it will also output the Rene number. So I guess we don't have it exactly at 4,000, but that's close enough. Okay, do we have any other numbers? Otherwise I have to start putting people on different jobs. Do we have anybody doing the very coarse ones? Maybe this one on the right here. Can I get somebody to do that? All right, good. Can I get somebody to do this number here? Anybody is free to do this field? Ben, okay, thank you. Anybody for here? All right. This one is what I'm running, okay. So refinement 4, and on the left, on the right? Your left, okay. It's also my left here. Okay. Right. What do you get? Are you still running? Okay. Good. Can I get somebody for here? For this field? All right. Good. Who has a fast computer? This one here? Okay. Very good. So maybe I should mark the ones I assigned. Oh, now I get pretty. Okay. You know, mine is probably close to done. So the thing I should do is that I should check how it's running. So I can plot this even while the computation is running, and you can see that this is already converged, right? We are pretty good, so I can just stop. So how do I stop this? I stop this by hitting Control C, and I'm just going to steal this number here.